All right, we're ready for round two. So the next speaker is Shih-Ping Lai, who will tell us about modeling the Goldreich-Kylafis effect.
Okay, so I'm Shih-Ping Lai from Taiwan. I'm from this National Tsinghua University. Some of you think I'm from HIA, which is in Taipei. It's very close. So if you have any chance to Taiwan, welcome to stop by. So this project, I work with my former student, Luz Yang, and then many collaborators are here. But first, before I go into my talk, I want to thank, Carl and Dick for establishing BIMA, because in the early days, 20 years ago, there's only 5 astronomers in Taiwan, and then some people think that we should do more astronomy in Taiwan. Then we invite some people from US. One of them is Frello and Paul Hall and Frank Xu. They look at sky in Taiwan and see, the weather is not good, so it's not good for us optical. Maybe we should think about radio. And the first project we have is this BIMA PhD fellowship program. I'm lucky to be one of them. In fact, all of this are still active in astronomy. First 4 are focused on star formation. This one, you may heard about him, Chao Lin Kuo. He had big news about the BICEP 2 last year. I wish he could learn more about that polarization, yeah. And following some success here, actually we have many people working on polarization observation in Taiwan. So all this have to thank, like I said, thank Carl and Dick for establishing BIMA. And in addition, I heard that, BIMA was expanding from 3 antenna to 10 antenna, and in early days, and the majority of funding is from, the insurance for the collapse of the 85 foot, right? So, I have to thank that moment seems to make my career and produce a generation of the people, astronomers in Taiwan. Okay, so I hope I didn't waste too much time. So now I'm going to talk about the Goldreich-Kylafis effect that hasn't been addressed too much in the previous talk. Basically, you can think about that the escaping probability, magnetic field is such a special force. When you look along it or perpendicular to it, you feel differently, right? So molecule and the atoms feel the same too. So they have a different escaping probability along it or perpendicular. Sorry, this is perpendicular. And so if you happen to be in an isotropic radiation field, you would generate some polarizations. This is first been proposed by Goldreich and Kylafis in the early 80s, but unfortunately it hasn't been detected for a long time, because first look at the equation. This is super complicated, okay? And the result, I don't know why it is missing here, but result is either perpendicular or parallel. It is determined by many factors, like a magnetic field and velocity and line of sight direction, all of this. So you don't know which one. So all the early attempts are failed. I think simply because you have if your beam is too large, you observe, you average out the polarization from the different region with different conditions. So actually, this is one of Dick's legacy here. But although early attempts are failed, he keeps pushing. So the first detection, actually this is first interferometric detection. The first single disk detection has happened in the same year, which is made with JCMT observation. But with interferometry, we can see much more detail because we have map here. I was went to the Illinois a little bit too late, so I missed out this opportunity. But this is a great detection to confirm this effect. Okay, but I did have part of my thesis working on this effect. I observed the DR21 OH in this Cygnus X filament, the brightest parts here. Why do I observe this? Well, I think I didn't know at that time, but anyways, it's one of the sources that Dick has strong detection, strong Zeeman detection, 0.4 and 0.7 milligauss. But with the polarization, you can see, well, this actually composed, it's a bit complicated. You can see the Y vector is from dust, and the black vector is from CO. Okay, both are in polarization direction, not magnetic field direction. You can see that this at many parts, those two polarizations seems to be perpendicular to each other, which fits theoretical prediction. But from here, you can also see that actually the magnetic field is a bit complicated. For the dust polarization, it is, well, there are some gap in between, and it changes from here to here. In fact, this is not just two cores, right? It's a very complicated region. With recent SMA result, you can see that these two cores actually contains many sources, about 9 or 10 source here. And our recent SMA observation shows that this dust polarization is very complicated here. But okay, I haven't talked about the CO polarization here. But for dust polarization, well, we have some discussion in the first day. You can see that if you look through a complicated region like the DR21 OH here, it's possible that along the line of sight you have different directions, right? And then you could average it all out, and so it's complicated. It's difficult to interpret the real direction in this source. But I just make it more dramatic. The real situation isn't that bad because what you measure is dominated by the polarization in the densest part. Okay, so with this Goldreich-Kylafis effect, we could possibly resolve the magnetic field direction in each channels, because the gas with different velocity is located at different positions, right, along the line of sight. So this is give us some hope to resolve the magnetic field along the line of sight. So after me, Polo, in his thesis, he also did observed sensors but different lines, and he found some interesting fact that the polarization in the 1 to 0 line is perpendicular to the 2 to 1 lines. It's almost perpendicular. This, right? So this tells us that actually different transition can give you different polarization direction. They make it even more complicated. And Polo make a nice program model to show that depending on the density, well, it could have perpendicular or parallel direction. So it can also transition from perpendicular to the parallel for different density and for different transitions. So now, right now, I'm going to show my this is recent result actually come with the dust polarization in the same data set. This is channel map, and the origin lines are the polarization directions from the CO322 data. So you can see that we actually have quite strong detection across many channels. That just show you that this is real signals. Just show you that this is the 5 position with the strongest signal. You can see that the Q and U are clearly detected. But we're not able to analyze the field channel by channel just because the signal to noise ratio. So we combine few channels to show you that in the blue shifted side and the red shifted side, the magnetic field or the polarization direction change dramatically. We compared it to the previous BIMA data, and we can get some results. Sometimes it's parallel, sometimes it's perpendicular. And we can compare to the 1 to 0 result, and this is 1 to 0 is perpendicular to 2 to 1, but 2 to 1 is parallel to 3 to 2. This is very complicated. You don't have to remember all this. But the last, I'll just show you the comparison with the dust polarization. Okay. So this color shows the angle difference between CO and the dust. And you can see that in the blue part, in blue shifted part, mostly the angle is about 0. It's a greenish color here. It's about 0. Here, maybe it has some strong outflow, so it can show you different color. But for the red shifted part, it's quite strange. This reddish color is 50 degree. So 50 degree. 45 is in the middle, right? 50 degrees is neither perpendicular nor parallel. So that's why we're doing this modeling business. It's a bit complicated. Actually, I'm going to skip all of that because my time is about to end. So I'm just telling you that we use the equation from the Deguchi Watson. And in that paper, there are two kinds of velocity structure. One is along the magnetic field line, one is perpendicular. We use a parameter to combine those both, so to simulate this outflow effect. We check our result. It's exactly the same as the Deguchi and Watson result. We play with the parameters. You don't have to understand all this. Basically, we play with the parameter. This just shows different conditions, different temperatures, different densities, and this is what is? Oh, this is different density. This is different background temperatures, and different velocity direction. So our conclusion is actually the CO polarization is following the dominant velocity field directions. So we look at the channel map, we think that this is most likely outflow because there are so many sources. The low velocity is complicated. High velocity, you can clearly see some high velocity collimated outflow. So we think that the CO in this CO polarization in this region may just follow the magnetic field direction. So with the result, we can show you that the CO are different from the dust polarization. So basically, we can, instead of just one layer, we can see 3 layers of magnetic structure here. Okay, so AMA will be good. That's my conclusion.
Okay, well done. So, okay, in the back, Martin.
Shih-Ping, I have a comment, and I think you know what I will say. You have to be very careful in trying to deduce the orientation of the magnetic field with line polarization, with Goldreich-Kylafis effect, because we know now that we'll often see circular polarization in CO, and it's due to conversion of linear polarization to circular polarization, and that rotates the orientation of linear polarization. So you have to first check Stokes V to make sure that it is not strong.
Yeah, I think I agree with you. For this data set and for the data set, and I think Daochong will talk about the IRAS-4A result later. Is our current accuracy, we could find that the inference of Stokes V is just roughly within the order of our measurement error in the angle. So this for this one, but I agree that it should be we should be careful to check every result.
Okay, so let's thank again.